Hello, so in today's class, let us now define what is called as Lebesgue measure. So we have seen what is an outer measure. So using outer measure, we will define what is Lebesgue measure. Now we have already proved that the collection of all measurable sets is a sigma algebra. So the collection of all measurable sets, so which we have defined by script M, is a sigma algebra. Now Lebesgue measure is defined as a set function which is defined on script M. So that is a sigma algebra. So that's a collection of all measurable sets. നമ്മൾ outer measure define ചെയ്യുമ്പോൾ M star is defined on any subset of real number. So it is defined on R. Now we will take a restriction of M star such that it is defined on script M. So this restriction of the outer measure M star is called the Lebesgue measure. So the Lebesgue measure denoted by, so we are going to denote it by small m. So the Lebesgue measure denoted by m is a set function defined on, so it's a set function defined on script m by, so the definition of the Lebesgue measure is, so m of e, so the Lebesgue measure of set e will be equal to the outer measure, so m star of e for all e belongs to script m. So Lebesgue measure is basically defined as a set function which is defined on script m, which is a collection of all measurable sets, which is a sigma algebra, and on script m the value of me will be equal to the outer measure. Now we know m star a is defined for all a contained in R and m star of a, so that is a set function which is defined on power set of R. And m star a is a set function on power set of R. Now as we know, script m is contained in power set of R and m of e, so the measure, the Lebesgue measure of e will be equal to m star e for all e belongs to script m. For all e belongs to script m, so therefore m is treated as, so m can be treated as a restriction of m star from power set of R to script M. So the Lebesgue measure is considered as a restriction of m star from power set of R to script M. So since it is a restriction of m star, all the properties satisfied by m star will also be satisfied by the Lebesgue measure M. So therefore all properties of m star is on measurable sets is satisfied by M. We will look at two important properties which are satisfied by the Lebesgue measure. So those are two propositions. So we will look at the first proposition. So proposition 1 states that, so let sequence ei be a sequence of measurable sets then the first part of the proposition states that m of union ei will be less than or equal to summation m of ei So this you can prove using outer measure, and using this result we will prove the next part of the proposition. So if the sets En are pairwise disjoint, so if the sets EA are pairwise disjoint, then M of union EI will be equal to summation M of EI. So the first property states the subadditivity, countable subadditivity. So M of union EI will be less than or equal to summation M of EI, and again in the sets En are pairwise disjoint, then M of union EI will be equal to summation EI. So for the first part of the proof, we'll use the fact that M star and എല്ലാ properties M satisfy the set of all measurable sets. Okay. So let us look at the proof. Now by the subadditivity of M star, so M star is subadditive. So by subadditivity of M star, so if you take M star of union EI, that will be less than or equal to summation M star of EI. Now all the EIs are measurable. EIs measurable ആണ്, അതുപോലെ union EI measurable ആണ്. കാരണം EIs measurable ആണെങ്കിൽ, since it is a sigma algebra, union EI, it will be closed under countable union. So as all EIs are measurable, union EI is also measurable. This is because script M is a sigma algebra. So if you take the union of any measurable sets, again the union is also closed under the union measurable. So now we are taking M star over the measurable sets. So if E belongs to script M, then in that case M of E will be equal to M star of E. So നമുക്ക് ഇവിടെ ഈ union of EIs E വരുന്ന EIs എല്ലാം measurable ആണ്. So therefore we can replace M star by M. So we may replace M star by M. This is because on script M they will be equal. So this gives, so this will give M of union EI less than or equal to summation M of EI. So this is the first part of the proof. Now let us look at the second part. Now for the second part, we will assume that all EIs are disjoint. So assume that EIs are pairwise disjoint. ഇനി pairwise disjoint ആണ് EIs. Now for each positive n, so if you look at union 1 to infinity, EI, so that will actually contain union 1 to n EI. So union 1 to n EI will be a subset of union 1 to infinity EI. So therefore by the property of measures, so if A is subset of B, then M of A, ഇത് രണ്ടും measurable sets ആണെന്ന് നമ്മൾ കണ്ടു. അപ്പോൾ outer measureന്റെ property അനുസരിച്ച് M star of A will be less than or equal to M star of B. So same property will hold for M also. So M of A will be less than or equal to M of B. So here M of union 1 to infinity EI will be greater than or equal to M of union 1 to n EI. Now this will be equal to summation M of EI. So summation 1 to n M of EI. Now this will hold for any value of n. So this is true for all n. So the inequality will hold when n goes to infinity. So let us now take limit n tends to infinity. So that will give us the required answers. So since it is true for all n taking limit as n tends to infinity, so take limit as n tends to infinity, so that implies m of union 1 to infinity ei, that will be greater than or equal to summation 1 to infinity m of ei. So this is the second result we have got. Now combining both the results. So ഇതിൻ കിട്ടി നമുക്ക് പിന്നെ നമുക്ക് first result കിട്ടിയത് m of union ei will be less than or equal to summation m of ei. So combining both we will get the required result. So combining 1 and 2. So combining 1 and 2 we will get m of union 1 to infinity ei, that will be equal to summation 1 to infinity m of ei. So that is the proof of the first proposition. Now let us look at the second proposition. So proposition 2 states that, so let sequence En be an infinite decreasing sequence of measurable sets, sequence of measurable sets, that is so En plus 1 is contained in En for each n, and let me1 be finite. Okay, so e1 ആണ് അതിനകത്ത് ഏറ്റവും വലിയ സെറ്റ്. So each en plus 1 is contained in en. So e2 will be a subset of e1, then e3 will be contained in e2, so on. So m of e1 is finite, then m of intersection 1 to infinity ei will be equal to limit n tends to infinity m. So the proposition states that if you have a sequence of measurable sets such that en plus 1 is contained in en, and if m of e1 is finite, then m of intersection of all ei's, that will be equal to limit n tends to infinity m of en. So let's look at the proof of the result. So let me put e equal to intersection 1 to infinity ei, then we can rewrite what we need to prove as, so we can write it as m of e equal to limit n tends to infinity m of e. So this is what we need to prove. Now let me define any oro each en plus 1 is contained in en. So let me define f1 to be e1 minus e2, f2 as e2 minus e3, f3 as e3 minus e4, so on. So in general, fi will be equal to ei minus ei plus 1. So for I equal to 1 to up to infinity. Now, so നമ്മുടെ sets ഇങ്ങനെ വരും. So if this is e1, then if this is the set e2, then e3, e4 ഇങ്ങനെയാണെങ്കിൽ ഈ ഇടയ്ക്കുള്ളതായിരിക്കും, ഇതായിരിക്കും നമ്മുടെ f1, ഈ ഇടയ്ക്ക് വരുന്ന സെറ്റ് f2 ആയിരിക്കും, f3 ആയിരിക്കും. Now this last one will be the intersection ei, so that will be equal to r e. So we have defined this to be f1, f2, f3. So you can, from the figure you can see that these fi's are pairwise disjoint. All fi's are pairwise disjoint ആയിരിക്കും. So all fi's pairwise disjoint measurable sets and we can see that e1 minus e will be equal to union 1 to infinity f. e1 minus e will be equal to union 1 to infinity fi. So idana intersection e nu parayunna idana. So Then you take E1 minus E, that will be F1 union F2 union